Welcome, ladies and gentlemen. So let's take a look at our vector valued functions. We need to be able to do kinds of particle motion things like find the distance traveled or the displacement of a particle or an object over an interval, the slope of a curve, or the speed of an object. So let's go ahead and take a look at these separately. Firstly, let's suppose that we wanted to write an equation for the line tangent to the curve at t equals 1, and we were given a parametrically defined curve like x of t and y of t. Then we'll switch over to our vector, right, notation when we deal with our particle motion. So we need the same three things that we've always needed to write the equation of a tangent line. We need the point of tangency, right, and we need the slope of the tangent line. Well, in this case, we're dealing with the point of tangency being an x comma y coordinate based on the parameter time t. So at t equals 1, we need to figure out the x coordinate and the y coordinate. And so we can do that with a straight evaluation of x of 1. So into my original, we'll do 1 minus 2 is negative 1. Quantity squared is 1. So raise your hand if you had x of 1 as the x coordinate. And pair that with my y coordinate of the object at time t equals 1 is given by 1 cubed is 1 times negative 2/3 is negative 2/3. So raise your hand if you have negative 2/3. Negative 2/3 is great. So we've got the x coordinate, we've got the y coordinate. What else do we need to write our equation of the tangent line? Danny?
Slope.
Our slope. So if we're given x of t and y of t, our slope is still the same dy dx from our Cartesian coordinate plane. But in order to find dy dx, we must consider the ratio of the rate of change in the y-coordinate to the rate of change in the x-coordinate. And so for us, our dy dx is going to be given by dy dt over dx dt, where dy dt is y prime of t, and dx dt is x prime of t. And so let's generate expressions for that. Dy dt is given by the derivative of y of t. And so what's that given as a function of t, Sydney?
Negative 2t squared
I'm down.
over 2t minus 2.
Yes, thank you. And the dx dt to boot. So we got the whole span. It looks like my dy, right, dx, then the slope of the curve will be given by this expression evaluated at the time value t equals 1. So we'll evaluate this at t equals 1. So we'll plug in and we get our final of 3 pieces for our equation of the tangent line. It looks like 1, is it negative 1? No? I'm bad with numbers. So this becomes 1 times negative 2 is negative 2. And then 1 minus 1, or 1 minus 2 rather, is negative 1 times 2 is negative 2. Oh, so positive 1? Are you guys getting positive 1? Yeah? Oh, good. Great, that works. So we've got our 3 things. We've got our x coordinate of the point of tangency, our y coordinate of the point of tangency, and the slope of the tangent line, which means we can go to our age-old classic point slope form, y minus y sub 1 is equal to m times quantity x minus x sub 1, and we'll simply replace our y sub 1 with the green 2/3, so y plus 2/3, our slope with the red 1, and our x coordinate with the blue 1, and we could make that look much prettier. We could do y equals x minus 1 and minus 2/3, so minus 5/3, right, if we wanted to. Y equals x minus 5/3. Cool. Raise your hand if you had the right equation of the tangent line. Great! And we would totally make a picture and look at the graph, right, if we had more time. Maybe we will, depending upon how it goes. But let's go ahead and tackle B then. So we need to be able to find the speed of the object at time t equals 2. Recall that speed involves the rate of change, right, in my y-coordinate and my x-coordinate as a function of time. And so speed, just like in the Cartesian coordinate plane, is the absolute value of velocity. So the first thing we can do is write our velocity vector and then consider the magnitude of that velocity vector, given that that's the absolute value of velocity. So we'll go ahead and generate our velocity vector. Think v. There's our thick v. And we can get our component form by doing our horizontal component. That would be the derivative of the x of t position. So that would be our 2 times t minus 2 to the first, comma, our horizontal, our vertical component rather. And that again is the derivative of my y of t function. And Sid told us that that's negative 2t squared. So there's our component form. Yes? If we wanted the velocity at t equals 2, then in component form that would be given by 2 goes in for t, 2 minus 2 is 0, times 2 is 0, so I'm getting 0 for my horizontal component. Is that what you guys got? And then my vertical component, 2 squared is 4, times negative 2 is negative 8. And so all we need to do now to get the speed is to take the absolute value of velocity. So we know that in general, the absolute value of velocity is given by our good old Pythagorean theorem, where we square the horizontal component, square the vertical component, add the two together, and take the square root. So it looks like just 0 squared plus negative 8 squared. And so we're getting square root of 64, so I'm getting 8. Raise your hand if you had 8. Anybody else get 8 for the speed? Good job, you guys. That's great. Which leaves us with 1 to go. Let's consider the total distance traveled by the object over the time interval 0 to 3. So just like before, in AB, we can get our total distance traveled by integrating the absolute value of velocity. It's just that now we're dealing with vector value function, where our velocity has components, a horizontal component and a vertical component. So what do we need to do? Well, we'll go ahead and integrate, right, over my time interval, the magnitude of my velocity functions, right? And so once again, that's going to be the square root of my dx dt squared plus dy dt squared. And so B and C are connected, but they're different, right? They're connected, but they're different. So let's go ahead and start with our general. The integral for distance traveled is given by our integral from C to D of the square root of, and we can write this in lots of different ways. We could have our horizontal component be d sub 1 of t. We could have it be x prime of t. Maybe we'll do that first. So we could have x prime of t squared plus the horizontal component be y prime of t squared, and then with respect to time. In this case, we're dealing with the time interval t equals 0 to 3. And so for us, we'll integrate from 0 to 3. The square root of, and x prime of t is given by my same old, is that the 2 times quantity, t minus 2. So that would be 2t minus 4, however you want to enter it in your calculator, plus my vertical component was the derivative of y, and that was negative 2t squared. So I've got negative 2t squared, and then that vertical component, rate of change in the vertical component is squared, and then close radical, and then we can integrate with respect to time. As I look at this, I'm thinking math 9, baby. And so I'm going to go to the grapher, and on my home screen, I'm going to math 9 it up from 0 to 3. And we need the square root of, and we need our horizontal, the rate of change in the horizontal component. Oh gosh, so I'm going to do a left paren, and then 2t minus 4, and then close, and then 2t. Oh, I know why, because I'm in polar form, because I was playing for today. So I'm not going to get like upset or whatever. I'm just going to go to the mode. It's all right. And I'm going to go parametric. And then I'm going to go back in there. And we'll see if it lets me. Will let me go. Will let me go T-style on that horizontal component? Yes, it will. And I'm still inside that radical, I think. Oh gosh, this is tough. Okay. Everybody okay? Everybody all right? Whew. I almost need the sweat man today. Tell you what. And negative 2t squared. Can I do 2t squared? I better not. Pains me. And then that's squared. And then I'm out of the radical. And then dt. Let's try. I'm thinking handful. 2 measure. And wow, that's what I got before. So raise your hand if you had 20.743. Yes! Hey! We're rocking and rolling with parametrics, right? We're ready to go and move on then to polar, and that's our subject for today. We're going to analyze polar functions, right? And so we're going to have a little review of what it means to be in our polar graphing mode, still be in the xy coordinate plane, and then we're going to find some area. Yes! I love it. So where are we? 20.743. But first, I want to make sure that you can get your test back, and we need to take care of our OTL number 2 check. And so this time I'm going to pause the recording, and we'll take care of that housekeeping. Okay, ladies and gentlemen, let's go ahead and redirect our attention to our note sheet. So we need to remind ourselves how it is that we handle, right, polar curves. And so let's take a look at our polar graph that's provided, and let's go ahead and plot and label the following points as our warm-up. So once again, remind ourselves how it is that we plot, right, when we're given polar coordinates. All right, well, our points are defined r comma theta, where r is the distance away from the origin, in the direction theta. This is where I start in standard position, right, where 0, right, 0 is pointing up along the positive x-axis and then rotating in the counterclockwise positive direction. So 3 comma 7 pi over 6, well, I would go a distance of 3 units from the origin along the ray given by direction 7 pi over 6. So if I start spinning, 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 this is pi, so 7 pi over 6 is here, and we'll go 1, 2, 3. So it looks like point A, I better do that over there. In blue, color coding, better do that over there. We don't think it's plotted point, should be 7 pi over 6 and 3 units. Yes, is that good? All right, let's go ahead and do green. For letter B, start at the origin and go a distance of, what? -2? How can I go a distance of -2? Well, I'll go in the opposite direction given by the ray 3 pi over 4. So where's 3 pi over 4? Well, 3 pi over 4 will be 1 pi over 1, 2 pi, so 3 pi over 4 would be this direction. I want to go the opposite direction 2 units, so how's that? Did I do it right? I'm sitting kind of close. Is that right? B? Yes, B? Point B. Yay! And we need one more. And why not do red for point C? Point C then says, let's go -1 in the, what? -1 comma 0. That's not xy coordinates. That's r comma theta coordinates. So I'm going to go in the 0 direction, a -1 unit. So it's right there. Is that right? Interesting. All right, so we've got point A, B, and C, and that's our quick and dirty review for graphing with polar coordinates. Very good? Moving and shaking then. Now let's go ahead and graph a polar curve, a function, right, whose independent variable is that direction angle theta, and whose function values are distances away from the origin, right, in the direction theta. How can we do this by hand? Well, so first we're going to do this by hand, and then we'll go ahead and experiment with our grapher. Well, we could go ahead and do what we did back from pre-algebra. When we first asked to make a graph, we constructed a table of values. It's just instead of having an x comma y table of values, we'll now have a theta comma r table of values. So let's go ahead and do that. And we may need to add, right, more values of theta, and their corresponding outputs are as necessary. If I'm doing this by hand, I'm going to try to make it easy on myself. As I go ahead and choose theta values, I'm going to try to make them easy to evaluate with the cosine function. So what will I choose? Well, I'll choose 0. Pi over 3 is easy to evaluate with cosine, right? So I'll choose 0, pi over 3, pi over 2, 2 pi over 3 is easy to evaluate. And pi, let's start with these values and let's see what we need to add in to get a nice picture. So here we go. At theta equals 0, cosine of 0 is 1 times 4 is 4, yes? So I'm getting 0. Oh, we want an arc on theta, don't we? I'm still going to apply arc on theta. I'm going to still evaluate my independent variable theta. So in the 0 direction, can we plot a distance of 4? Certainly. 1, 2, 3, 4, tick. How's that? Second. In a distance of pi over 3, can we plot cosine of pi over 3 is 1/2 times 4 is 2? Are you guys getting 2? So can I plot in the distance pi over 3, 2 and 2? Yes? And the distance pi over 2 would be straight up. I'm going to plot cosine of pi over 2 is 0 times 4 is 0. Huh. What would that be? 0 units away from the origin would be right there. Yes? Negative 2 pi over, oh, why did I say negative 2 pi over 3? I don't know why. I don't know why I should swallow this off. 2 pi over 3, cosine is negative 1/2 times 4 is negative 2. What? Can I go negative 2 in the 2 pi over 3 direction? 2 pi over 3 would be here. Negative 2 would be along this ray in the opposite direction and be there. You guys getting that? And then back when theta is pi, cosine of pi is negative 1 times 4 is negative 4. So when we're at pi, we're going to go the negative. So that falls on this point again. So any ideas of what this is going to look like? Should we pick another value of theta? Let's pick a, we'll pick a pi over 4. So I pick pi over 4, cosine of pi over 4 is root 2 over 2 times 4 is 2 root 2. And root 2 is about 1.414. So that would be 2.828. So let's go pi over 4 direction, 2.28. Oh, I see. And if I chose 3 pi over 4, if I chose 3 pi over 4, cosine of 3 pi over 4 is negative root 2 over 2 times 4 is negative 2 root 2. Negative 2 root 2 would say go in the 3 pi over 4 direction, a distance of negative 2 root 2, so that would be negative 2.828. So negative 2.828. So here, all right. So I'm getting a pretty clear picture. If we continue choosing theta values and evaluating, we get what shape? A circle. A circle. Absolutely. Oh gosh. All right. Let's go ahead and try to recreate that now with our grapher. We're going to do this in polar mode. So everybody, let's see if we can't recreate this in polar mode. So here we are, and we have 1, 2, 3, negative 4, negative 4, and so I'm going to window. We made it with 0 to pi. I'm going to leave it 0 to 2 pi for a minute. Negative 4 to 4, and negative 3 to 3. I'm going to try that and see what happens. So I'm going to see what happens with this. When I go to my y equals, notice how my function menu gives me r equals. So r sub 1 is our first curve. I'm just going to enter 4 cosine theta, close input, and let's see what that looks like. Hey! Now it went around a couple of times. How come? Well, it looks like cosine completed its cycle there, right? Once it got to the negative values, it was going in the opposite direction. So we were able to complete one full circle in the theta range from 0 to pi. So in my window, 0 to 2 pi, it traces the circle out how many times? 2 times. And so we saw that when we graphed that little ball went around 2 different times. When we're working with polar curves, I encourage you to use the little ball line style so that you can see that it's retracing. If you don't change it to the ball line style and just the curve, you're not sure how many times it's actually going around with just a line. So by doing the ball, you can see exactly how many times it goes along. And that's going to help you find the intersection of curves when we find the area between them. So that's kind of where we're headed. Cool. So not too shabby. And then I could change my window to square if I wanted to make that circle look, right, more circular and less like an ellipse. But I did this window here. All right, so does anybody notice anything about my equation and the circle's physical characteristics? Well, my equation in polar form was r equals 4 cosine theta, and clearly we generate a circle. So what are a couple of things about my circle? Right, what about the size of it? Sophia?
The diameter is also 4.
Yeah, the diameter of my circle is 4, which means the radius is 2, right? The square root of that 4 is 2. And the orientation, right? The orientation of my circle shares that horizontal axis symmetry, top-bottom symmetry, right? Top-bottom symmetry along the horizontal axis. I'm just, while we're here, right? While we're here, what would have been different if we had this be for sine theta, right? What would have changed on my graph? Courtney?
It would be symmetrical along the y-axis.
Absolutely. We'd have left-right vertical symmetry. So a quick check. And Courtney's absolutely right. You see that? What if we had negative 4 sine theta? What would that have done for us? I don't know. Let's see. So now we're still left-right. I'm sorry. Along the vertical axis, left-right symmetry, right? You see that sign represented the vertical displacement in my original Ferris wheel, but now we're down below it. So you see how the connection between our Cartesian transformations reflect in the polar coordinate system. All right, let's go ahead and grab this bad boy by hand. So can we try and do this? Yes, we can. So let's go ahead and do this again by hand, and then we'll verify with the graph. So we are thinking already, right? I'm going to have some symmetry here. We're going to have left-right vertical axis symmetry. So we should have left-right reflectional symmetry somehow, right? With this, let's see how we can get some points here. So once again, I'm going to choose theta values and pair them with output r distance values from the origin. And we're going to try and do this by hand. And I'm not sure how it's going to go, but we're going to do our darndest. And so let's see, 0. Sine is easily evaluated, right? Sine is easily evaluated at pi over 6. And if I want to go right to the power of 4 already, or if I want to wait. I'll go. I don't care none. Pi over 2. And 5 pi over 6. And pi. Let's see what this produces so far. So in the 0 direction, right, we're going to go a distance of sine of 0 is 0 times 2 is 0 is 1. So in the 0 direction, I'm going to go 1. Very good? Yes. Pi over 6. In the pi over 6 direction, I'm going to go a distance of r equals sine of pi over 6 is 1/2 times 2 is 1, and 1 minus 1 is 0. Are you guys getting 0? So in the pi over 6 direction, I'm going to go 0. Oh, I should have made it smaller. The pi over 4 direction. The pi over 4 direction. Sine of pi over 4 is root 2 over 2 times 2 is root 2, and 1 minus root 2. Oh, this feels familiar. 1 minus root 2 is 1 minus 1.4 is negative 0.4. Huh? Can I do an about? So in the pi over 4 direction, I'm trying to go negative 0.4. I wish I made it bigger scale here. Pi over 2 direction. So pi over 2 is sine of pi over 2 is 1 times 2 is 2, and 1 minus 2 is negative 1. So the pi over 2 direction we're going negative 1. Yes? 5 pi over 6. Oh, goodness. So sine of pi over 6 is 1/2 times 2 is 1, and 1 minus 1 is 0. So in the 5 pi over 6 direction, that's here. I'm going 0. Uh-oh. And pi. What does this look like? Sine of pi is 0 times 2 is 0, and 1 minus 0 is 1. From the pi direction 1. How's that? Is that better? All right. So I'm having a hard time visualizing what this looks like. So what do we need to do? Maybe we need more points. Yeah? All right. So what do we need? Well, let's keep going with our circle. So let's choose 7 pi over 6. 3 pi over 2. And 11 pi over 6. And pair them with our corresponding outputs. And pair them with my corresponding output. 7 pi over 6 sine is negative 1/2 times 2 is negative 1 minus 1 is 0. That doesn't add anything either. Here again. 3 pi over 2 sine of 3 pi over 2 is negative 1 times 2 is now we're talking. Is negative 2, and 1 minus negative 2 is 1 plus is 3. You guys get that? Oh, now we have something going on here. So here, and 11 pi over 6. The sine of 11 pi over 6 is negative 1/2 times 2 is negative 1, 1. Oh, I know. It's
Yeah, there we go.
2. That's way better. So this is also positive 2. So 7 pi over 6 is 2. Oh, that's way better. Negatives are hard. Is that better? Oh! I think I know what this looks like now. That's way better. 11 pi over 6. In this direction, 2. Hey! Alright. So the good news is, on the AP exam, right, you'll be able to use graphing calculator when you construct polar curves that are cardioids, limazons, and lemniscates. So you'll be able to use your graphing calculator when you have the little loop-de-doos, all right? So that's helpful. It'll also be helpful for inspection when you're finding your limits for integration for area. So let's go ahead and see if we can connect these. It looks to me like we're going to have a loop there. Can I go for it? I am. I'm going for it anyway. Oh, gosh. Oh, geez. Oh. All right. I can't take it any longer. Let's go ahead and check. Ready? 1 minus 2 sine theta. And I did 0 to, we did all the way to 2 pi this time. All right, so let's see what happens. There it is. There's a loop. Oh my gosh! That's not too shabby. If I could only add and subtract positives and negatives, we'd be set, right? Woo! Good heavens. Okay, so we've reminded ourselves about graphing in the polar coordinate plane. And now let's remind ourselves about some conversion formulas. So our conversion formulas, right, come directly from Pythagorean theorem and the relation between Cartesian point, comma y, and, right, that angle theta, your direction angle. And so, what is the x coordinate given by? Well, it's given by r cosine theta. Where cosine theta, right, is still a measure of the magnitude of my horizontal displacement x divided by the distance r, that the hypotenuse in my right triangle. So what do you think y is? Well, you know that's r sine theta. Then our Pythagorean theorem, right, holds true. X squared plus y squared must equal what? R squared. Again, because r is the distance from the origin, that's like the hypotenuse of my right triangle. Tangent of theta would be given by my ratio, vertical displacement over horizontal displacement. So for us, that would be y over x. 20. All right. Let's see. We need parametric equations of polar curves. Yes, we do. So we saw that x is given by r cosine theta, and we'll now let our generally defined, right, function be given by f of theta. So let's rewrite this same thing, x equals r cosine theta, but now we'll start substituting in my function f of theta for my r value. So this will be f of theta times cosine of theta. Applying the same reasoning will generate our y coordinate, r times sine of theta. Will now be given by f of theta times sine of theta. We will hold off on slope, and we'll see if we can generate the same thing now in parametric mode using our f of theta cosine theta, f of theta sine theta for the x and y respectively. So let's go ahead and try this. In our calculator, let's go back to parametric mode. Everybody mode, and let's do parametric. And let's go ahead and see if we can't generate that original circle. But now when we have a function x and y defined parametrically with theta as our...
Pardon the interruption for today's morning announcements.
Forgot that.
It's Tuesday, April 18th,
How come?
and it is A-Day today. The lunch menu on the premium grill is a smash burger on a brioche bun with cheddar or pepper jack cheese and french fries. Chef Brian has a half sandwich and soup bar. You can select from a variety of soups and sandwiches to create your ideal combo. Also offered today is pizza, fried chicken sandwich, mini corn dogs, and made-to-order pasta bar served with a fresh salad and garlic breadstick. Please rise for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Attention Coco Pelli customers, this week's Coco Pelli drawing winners are